So let's go back to an old familiar, a dice problem. So here's the setting. Imagine that one has a pair of dice. One die with 5 red faces and 1 white face. Imagine that this one has a white face, perhaps towards me so you don't see it. And one die with 5 white faces and 1 red face. Imagine the red face is concealed from you. We have 2 dice. A die is chosen at random. Now, what does it mean? Well, imagine that you have a fair coin and you toss it, and if it comes up heads, you select the die which has 5 red faces and 1 white face. If it comes up tails, select the die which has 5 white faces and 1 red face. Good. Once you've selected a die, you throw it twice and observe the face that shows up. The question at hand, what is the chance that for the chosen die, you're not told which it is, that given that the first throw shows a red, that the second throw also shows a red face? Pause and think about this for a minute. See what your intuition tells you. Of course, we are going to put together a formal framework for an analysis of this elementary problem. Now, the problem setting that I have given you can morph into many other mathematically equivalent but formally different settings. For example, we could replace the 2 dice by an urn and ball problem. Imagine one has 2 urns. In one urn, there are 5 red balls and 1 white ball. And in the other urn, the second urn, there are 5 white balls and 1 red ball. An urn is selected at random, and then balls are drawn from the selected urn, sampling with replacement. Given that the first ball drawn is red, what are the chances that the second ball drawn is red? We could replace the urn and ball metaphor, for example, by a coin metaphor. Imagine one has 2 coins. One is biased 5 to 6 in favor of successes. The other is biased 1 to 6 in favor of successes. A coin is selected at random and tossed twice. Given that a success occurs in the first trial, what are the chances of a success on the second trial? Settings like this inform a variety of problems, and we'll see application domains in epidemiology, for instance, which draw upon such simple urn or dice models. But to come back to our problem. So imagine again we have our 2 dice. We've selected one of them at random and we've thrown it twice. What are the chances that the second throw results in a red face, given that the first throw has given you a red face? Well, naturally enough, we should begin by constructing a sample space for the problem. Now recall that one constructs a sample space by identifying all chance-driven elements and then encapsulating our understanding of all that is uncertain in the experiment in some simple and evocative notation. Now, in our setting, there are 3 elements that are chance-driven. First, the selection of the die. Second, the outcome of the first throw. Third, the result of the second throw. And so, to completely specify an idealized outcome for this experiment, one has to specify a triple of possibilities. The selection of the die, 1 or 2, and the results of each of the 2 throws. Let's say that we call such a triple, identify it by 3 letters, X, Y1, and Y2. Of course, you'll notice there's a semicolon after the X. This is purely for visual purposes. There is good notation and there's bad notation. The best kind of notation is evocative. It clarifies and brings to the fore the key elements of the problem. Poor notational choices obscure and confuse. Now, in our setting, we have 3 elements, and to visually distinguish the different flavors of chance, in the three elements, we utilize different letters. X for the coin toss which selects the die, and Y for the face of the die that results. We use a semicolon in addition to separate these chance elements to visually tell us, there are two different pieces of chance going on in this conjoint experiment. Now the sample space is a space of all such triples where X takes one of two values, 1 or 2, representing the two dice, and Y1 and Y2 take values either red or white, and we abbreviate it, of course, naturally, by R and W. What are the events that are of interest to us? Now, on consideration, it becomes clear that for our problem, there are two events of interest. An event that the first throw of the randomly selected die is red. Let's call this event R1, the subscript 1 connoting the first throw, R, of course, connoting red. R1, then, is a subset of the space of idealized outcomes. It's a subset, a subcollection of triples X, Y1, and Y2, with the property that Y1 is red, and X and Y2 are unfettered. Similarly, a second event of natural interest in this problem is R2, the event that the second throw of the die results in a red face. What is R2? It is that subcollection of sample points, that subset of triples X, Y1, Y2, where the third element, Y2, is red, and X and Y1 are unfettered. They can be anything. Now, before we go launch into an analysis, into a calculation, we should pause and think about the problem. Is there a way of partitioning it in a reasonable way? And the notation makes clear that there is indeed a natural partition for this problem. Is there an ancillary event of interest to us? Naturally enough, on consideration, we realize that the entire game seems to hinge upon which of the two dice is selected. And therefore, we introduce a third event, an ancillary event of interest in this problem. Let's call it A. This event is going to encapsulate side information about the problem. Let A be the event that the first die is chosen. Let's say the die with 5 red faces. And let A complement, therefore, represent the event that the second die is chosen, that is, the die with 5 white faces. We are now equipped to do a computation. We've identified two target events of interest, R1 and R2, and potential events which can function as ancillary events conveying side information, the events A and the complement of A. What now is the probability measure? Now, there are several ways of approaching this problem, but perhaps the most natural is to specify the probability measure implicitly via certain natural probabilities we would like to associate with certain events. So let's begin with the selection of the die. Random selection means one is going to flip a fair coin, and if it comes up heads, pick die 1, and if it comes up tails, pick die 2. Naturally enough, I want to allocate to both possibilities equal chance, and therefore the probability measure, whatever it is, should allocate to A and A complement both probability 1/2. Very well. How do we proceed? Now, once a die is selected, now there's no ambiguity about which die is selected. I picked up die 1 with 5 red faces and 1 white face. Now the chance experiment is very, very clear. For this die, the chance of throwing a red face is naturally 5 in 6. There are 5 red faces, one white face, and therefore the chance of throwing a red face, given that I have selected this die, is 5 and 6. And therefore, the chance of throwing a white face, the event A complement, given that I have selected this die, is 1 in 6. Now, what are the chances of throwing two reds in succession? Well, there are 5 possibilities for the first red face, 5 for the second red face, and therefore, by the elementary principle of counting, 5 times 5, or 25 possibilities for selecting the pair of red faces. Out of how many possibilities? 6 times 6, or 36 possibilities for the arrangements of the two faces. And therefore, the chance of throwing two red faces in a row for die 1, given that die 1 is selected, is now 25 and 36. And by an identical calculation, the chance of throwing two red faces, given that die 2 is selected, well, if die 2 is selected, there's only one red face, and there's only one way of throwing the same face again. And therefore, the chance of throwing two red faces in a row, given that die 2 is selected, is now 1 in 36. Of course, you can build other conditional probabilities along these lines. Now, with this in hand, we are in business. We've got at least implicitly a probability measure at hand, and now we want to compute, say, the probability, the chance that the first throw of the chosen die results in a red face. Pause for a minute and see, without doing any calculations, what your instinct tells you. Now, when you're ready, how do we partition the problem? The event R1 stands in the role of the target event H in our definition of conditional probability. The events A and A complement stand in the role of ancillary side information, which conditions the occurrence of H. And by the additivity principle, we simply write down the additivity property for conditional probabilities, and we find we have a very, very simple expression. Compute it, and we find there's a 50% chance that the first throw results in a red face. Introspection says, well, that's very natural. I have two possibilities, and they're so symmetric. 5 red, 1 white, 5 white, 1 red, pick one at random. There should be a 1 in 2 chance of getting a red, and indeed there is. Let's take a slightly more complex question. What are the chances that the first 2 throws both result in a red face for the chosen die? I've not told you what the die is. What does instinct tell you? Well, raw intuition might say, look, throwing the die once is as if I had a die with 3 red faces and 3 white faces. I threw it once, and the chance of getting a red is 3 in 6, or 1 in 2. If I were to throw it twice, the chance of getting a red should be then 9 in 36, or 1 in 4, 25%. Now, let us see what our calculations give us. Now we have a more complex event, a conjoint event. I want the first throw to result in a red face and the second throw to result in a red face. We are looking at the intersection of the two events, R1 and R2. Now, R1 intersection R2 stands in the role of H in our definition of conditional probability, and we partition the space again by A and A complement depending on which die is chosen. We write down the definition of conditional probability. Pause, write it out. Make sure you absorb this. Write down now numerically what we have in our implicit definition of probability measure. Work your way through the fractions, and we find that the chance of seeing 2 red faces in a row is about 36%. Significantly more than the 25% I might have naively anticipated in an equivalent experiment, which turns out not to be equivalent after all. This suggests that there are pitfalls here. There are pitfalls for the unwary, that we should be cautious in setting up the experiment. And this points again to the salutary value of setting up the sample space carefully, setting up the events carefully, setting up the probability measure carefully. We now have two probabilities, the probability for R1 and the probability for the intersection of R1 and R2, and we're all primed for a conditional probability. Write down the definition of conditional probability as the proportional chance of R2 in R1. Write down what we observed, work our way through, and we find the chance of a second red, given that the first throw resulted in a red, is quite alarmingly large. It's about 72%. That sounds remarkable, given that on any given throw, the chance of observing red is 50%. This sounds strange and wonderful. How did the chance jump from 50% to 72%? Well, conditioning does affect raw probabilities in frequently unanticipated ways. Of course, once we have an answer, we can look back at the problem and figure out what went wrong with our raw intuition. On consideration, we realize that when a red face is seen, since a red face is so much more likely if the first die is thrown than if the second die is thrown, the occurrence of a red face suggests that there's a likelihood that the first die is a die being thrown. And of course, if it is the first die that is being thrown, the chance of another red face is quite high. And therefore, our raw probabilities increase via this conditioning. Now, this is a salutary example. It's elementary. There's nothing deep about it. But it serves as a useful vehicle to reinforce the basic definition and the key principle of additivity melded with the definition of conditional probability via chaining. Right? Stare at this example, work through the probabilities again carefully, settle the concepts. These ideas are going to become repeatedly useful.